Hello and welcome to a new session for this online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre. Today we are going to look at a very different topic. Although we mentioned this topic in the first lecture where we were talking about various ways of implementing the embedded computers, and to revise that or to mention what we had repeat what we had mentioned. We had said that there are three ways of implementing an embedded computer. The first method is using a general purpose computer plus processor. The second is to use an application specific processor. For the first approach, you might be using commonly available microprocessors such as 8086, 68000 and so on. For the second approach, we would be using a microcontroller, which is what we are doing in this course. But we had mentioned a third approach, and this was called single purpose computers. Which means computers which are designed with only one objective in mind, which is to solve the current problem at hand. It cannot do anything else. If you want to modify it, you will have to redesign everything. Usually these single purpose computers are implemented using digital logic, and it follows a paradigm which we also showed how that paradigm of looking at the computational model applies to the general purpose processor as well as the application specific processor. That paradigm included two building blocks. One was called the sequencer or the controller, and the second was called the data path. The sequencer decided which elements of the data path to be used for what computational tasks. The elements of data path would perform their tasks, process data as they are capable of, and convey the result or parts of the result to the sequencer to decide the next course of action. In this lecture here, I am going to show you a sample project implemented using such an approach. The heart of a single purpose computer is the finite state machine. This finite state machine is a computational model with which you can create sequences. It uses a concept called states and outputs and conditions of transition. When a certain machine has characteristics of switching into other states in accordance with its inputs, pass status, clock signals, these class of machines are called finite state machines. They are known by other terms also, such as finite automata, sequencer, as we will be using that term often in this lecture, or control path. Now, broadly there are two types of finite state machines. One is called the Moore machine here. The characteristics of this Moore machine is that the machine output depends only on the current state. So, the representation of the states, outputs and the transition conditions are illustrated using a diagram called state diagram. So, here in this machine there are two states. One is we could call it S0, state 0, and another is state 1. And if you are in state 1, state 0, then it would produce certain outputs which you can define here. We have just given a label output, but you can mention what all outputs you have, what is the values of those outputs, 0, 1, whatever. And then when a certain condition is true, here it should be that if the condition is say not true, then it will remain in this state, but if the condition becomes true, it will transition to S1. Similarly, we could make it that if the condition is true, it remains in this state, but if the condition becomes false, so I have used a condition bar, it will transition from S1 to S0. This is the complete description of more state, more type of finite state machine. There is another method of modeling state machines, and that is called Mealy machine. In Mealy machine we have the states are still the same, but now the outputs have moved from within these states, these circles which represent the state, on the edges which represent the condition. And again I will have to correct this. Here is the condition bar, and if there is condition, then say I can say output 1, this is output 2. If it is condition, you remain in. So, this is states S0, this is state S1, and for condition 1, and you could have output 2 here, it continues to produce output 2, and if it goes back here, it could be output 1 again, and it goes back into state S0. This is the graphical representation of any finite state machine. As you can see, it uses two symbols. One is a circle to represent the state, and one is these arrows which represent the transition conditions. These transition conditions are basically inputs, which when they change, they transition from one state to another state. However, one must also keep in mind that if these finite state machines are implemented using a synchronous logic, then the transition happens on two conditions. One is this condition being checked, but also at the rising or falling edge of the clock, whichever may be the case in your implementation. So, it requires two conditions to be true: the physical condition, that is the input to have a certain value, and the transition of a clock from 0 to 1, then only it will transition from state S0 to S1. This must be kept in mind. It is not mentioned here, but this is what is the assumption. The physical representation of such a state machine can be done by using three building blocks. One of them is the memory. As you see here, this is the memory. This is the combinational logic, and this also is. So, this I would say combinational logic 1, and this is combinational logic 2. The combinational logic receives the inputs. These inputs are external inputs, which means we call them asynchronous inputs, which means they are coming from an outside world, outside of this system, and therefore, they can change whenever they wish to. They are applied to this combinational logic block. This combinational logic block produces an output which become the input of the memory. And so, this is, since this is the value that is currently known, this is called next state. I will come to that in a moment. The output of the sequential logic, which could be implemented with D type flip flops, is passed through another combinational logic block, and that produces the output. And since we said in the Moore machine, the outputs are dependent only on the present state. So, this is your present state. The combinational logic does not change the state, it simply transforms these present state values into expected output. And these are the outputs that you mention in the circles that represented each of these states. These present state values also are fed back into the first combinational block, and together with the inputs they decide the next course of action, that is, it provides next state inputs. And as you see, the memory is clocked, and this clock is locally generated, and the rate of this clock will decide how quickly this state machine can transition. All of this can be implemented using logic circuit. This is combinational logic, this is memory, that is flip flops, and this is another set of combinational logic. Now, in this block diagram, if you want to represent a Mealy machine, all you have to do is the inputs now are able to affect the outputs. Not only the outputs are affected by the current state, but current inputs may also modify the outputs, and this is represented in this second diagram here. As you see, rest of everything remains the same. This is my next state, this is my present state. That present state is being fed back into the combinational logic, but some or all the inputs are being fed into the output combinational logic, and therefore, these outputs are dependent not only on the present state, but also on the present inputs. and these are two alternative methods of implementing the finite state machine using the Mealy model or the Moore model. Now, when you probably would study this as part of digital circuits and systems, and they would talk about various examples, and I want to take one example. What are simple examples that you already know? A counter is an example of a finite state machine. It has finite number of states which can be limited by the maximum number of flip flops being used in that counter, and so the state diagram can be drawn to represent the transition of the states, that is how the counter is working. Is it counting up or is it counting down, or is there any sequence in up or down sequence, or you want to change that sequence? You can create a counter with arbitrary outputs also, outputs that do not seem to have a pattern of being increasing or decreasing. You can choose that, and let me show you an example of a finite state machine. Essentially it is a counter, except with a little addition, that I have added a enable signal. If the enable signal is 1, it transitions from one state to the other. If the enable signal is held to 0, it will retain the current state, and if it retains the current state, it will keep on producing the outputs as mentioned in the state circle, in the symbol that represents the state. Now, how do you implement such a finite state machine? How do you implement that counter? Now, you can actually draw from the state diagram, you can create a state table. In the state table, you will create a table. Let me show you what that table would look like. In that table, you will create what is your present state, we call it PS, what is your next state, and what are the outputs. And if it is a Moore machine, then the outputs can be mentioned as a function of the states only. So, if I know my present state S0, I know my output. So, maybe output 1, and my next state could be S1, and this is if my present state is S1, the next state is S2, and you can have output 2 and so on, and eventually it will somewhere it will say, let us say S7, and I want to go to S0, and it will output will be OP7. Now, with this table I have actually represented a counter with no enable signal. Okay. Why? Because whenever you are in state S0, the clock will take you to S1. If you are in S1, it will take to S2. There is no condition to hold the current state. If you want to modify it to be representative, this is the state diagram, this is a state table from the state diagram we drew earlier. If you want to create the state table for the earlier state diagram, then it will have to have the following representation. So, this is still your state table. Here you will write present state, and if the input which is enable, if it is 0 and if it is 1, because there is only one input, what will be the next state, and here is your output. So, if the present state is S0, if the enable signal is 0, the next state will be S0. However, if the enable signal is 1, the next state will be S1. But if you know S0, you can say I want the output to be 0 0 0. If the present state is S1 and if enable signal is 0, it will retain that state, and if it is 1, it will go to the next state, and I can have my output 0 0 1 and so on and so forth. Now, once you create this state table, you know the relationship between the inputs and outputs of your first combinational block, the relationship between inputs and outputs of your second combinational block, and the middle block is just few flip flops, and we can decide how many flip flops to use. One method is, for the total number of states that we have, we take log 2. So, like we have 8 states, you take log 2, you get 3. So, all you have to do is use 3 flip flops. This is the encoded method of representing the states. The other option is for all the states you have one flip flop, and that is called one hot method of encoding representing the state. We are not going to go there. It may appear that a one hot encoding uses more memory, but the advantage of that oftentimes is that when you use more memory, your decode logic, that is the first block of combinational circuit, maybe even the second block of combinational circuit, the complexity of that circuit will simplify. So, it is a trade off. If you use the encoded method, that is use less number of flip flops, your combinational circuit might increase, and so you decide whether you want to use the combinational the encoded method of state representation or the one hot method. Anyway, this can be manually implemented, meaning you could create a table which implements the relationship here between inputs. Now, your input here is enable as well as the present states, and you are producing next state. So, if I use the encoded method, the number of flip flops will be 3. Therefore, you have to deal with 3 D type inputs to the flip flops. We can label them D0, D1 and D2. The outputs of these flip flops will be Q0, Q1 and Q2, and these outputs here they go into the combinational circuit, including the signal enable. So, you have to create a table which has Q2, Q1, Q0 and enable to produce outputs which is D2, D1 and D0, which means it is a matter of implementing 4 combinational circuits with 16 states here. These 16 states will produce one output, the same 16 states will also produce another output and the third output, and that resultant combinational circuit logic circuit will go in the first combinational block 1. So, here you are putting En enable, you are also putting Q2 and it is producing D2, D1 and D0. So, implementing a finite state machine is an exercise in starting from creating the state diagram, from there to create the state table. That state table will give you the relationship between inputs of the combinational circuit and the outputs. It will also give you another relationship for the second building block combinational circuit 2. The inputs to this will be Q2, Q1 and Q0, and the outputs will be say O2, O1 and O0. So, you solve this combinational circuit using minimization techniques that you are aware of. You solve this combinational circuit using the same approach, and the middle path is just a sufficient number of D type flip flops. So, you see implementing a finite state machine is all about implementing a couple of combinational circuits. Now, this is possible manually using pen and paper method if the number of inputs on your combinational circuit are few, meaning 4 or 5 or 6, because with 4 inputs you can you can draw a K map, but as the number of inputs increase, then you may have to resort to other methods, and in the contemporary world this is only for learning purpose. Real implementation is done with the help of representing the requirements of this state machine as a hardware description language code. So, I am going to show you that for this counter what kind of VHDL code is implemented. Here is the VHDL code. Here, as you are aware, VHDL code consists of 2 parts: the entity declaration here, which defines the relationship of this circuit with the outside world. So, in this case the entity will have all those signals which enter the circuit and which exit the circuit. In our case, we have clock and enable signal, and the outputs are these actual outputs which are the output of the counter. And then the second part of a VHDL code is the architectural description, architecture block, which decides the relationship between these input signals and the output signal. And you can express that in various ways, various methods of writing your code. One of a common popular method is called behavioral style of modeling. In this you have represented your code, and once this code is compiled, it will give you a net list of components or digital logic building blocks, which when connected as the netlist suggests, it will implement a 3-bit counter. Now, what can I do with that counter? Let me show you an interesting variation to that counter. We have a counter with 3 outputs, and it uses all the possible states, that is going from 0 0 0 to 7. So, essentially what was implemented was an up counter with an enable signal. Whenever enable is 1, it will transition to the next state. If the enable is held to 0, it will become it will hold that current state. Let me say that I modify that counter to not have 8 states, but have only 6 states, say 1, 2, 3, 4, 5 and 6, which means it will still require 3 D type flip flops, because the number of states is more than 4 and less than 8. What would I use that for? I could use this circuit to actually implement a dice. How? So, it is like this, that I have created a counter. The counter requires a clock, yes, it can be a high frequency clock, but now I have a enable signal in the following form. I have VCC, I have a switch, and I have a pull down resistor, and this is going into the enable signal of the counter. Now, since this is 0, it is going to hold the state. This 3-bit, we will call it 3-bit dice counter. The outputs are, let us say y2, y1 and y0. So, there are 3 outputs, and the state diagram for this is as follows. You have 1, 2, 3, 4, 5 and 6 states. If the enable signal is 0, so enable bar, it is going to remain in that state, this is S0. Now, I can choose whatever outputs I want in those states, and I want, because the dice will give you random numbers between 1 and 6, I want in the first state it to give me 1, 2, 3, 4, 5 and 6, and if the enable signal is 1, it goes to the next. Here again En bar, so it is S1 En, here En bar, again this is S2, S3, S4, S5, En, this is going to stay here for En bar, En, En bar, En, and I am going to stay here for En bar. Now, basically what I have done is I have repurposed that counter to become a dice. The only condition is that the clock frequency should be very high. Now, when a user presses the switch, the counter will start working, it will go transition through all these states, and when I remove the switch press, when I release the switch, the enable signal will become 0 and it will hold a state where it had reached, and those outputs will become stable. Now, these 3 bits can be decoded, passed through another combinational circuit, and can be represented on a 7 segment display if you like. And so, what you have done is started with a simple state machine, finite state machine, and converted into a useful piece of equipment or gadget. However, please understand that this is not really what a full computer would do. This does serve a purpose, but this is very simple applications. In real applications, the finite state machine is only a sequencer, which means it tells somebody what to do, and that somebody has to actually perform those operations. In this simple application, the sequence itself could be converted into numbers, but nothing more. right. And so, what we are going to look at is a bigger model where we are able to not only decide the sequence, we can program what sequence we want by implementing the state machine, and we have other elements of data processing which are under the control of the outputs from the state machine to perform useful computational operations. And that approach involves a building block which we call as the data path. So, data path is nothing but it represents all the functional elements which process data which are under the control of the finite state machine, and when you glue these two building blocks together, one which consists of the sequencer or the control path and the other which consists of data path elements, then you are able to implement a single purpose computer, and that is represented or that is called FSMD, that is finite state machine with data path. Finite state machine sequences operations into data path through signals called control signals. The data path elements under the control of these control signals perform certain useful operations. They may give the feedback back to the sequencer using what we call as status signals, and the happy marriage of these two elements will be used to implement a single purpose computer. So, we need to send control signals to the data path from the sequencer, and the data path will need to perform useful operations and give feedback to the sequencer so that the sequencer can decide what is the next course of action. Here is a block diagram. This is a repeat of what I had shown earlier, that we have a sequencer which is nothing but a state machine, and the state machine produces control signals and feeds various elements of data processing elements, and here is a list. I will show you a bigger list. These elements will operate on that data which may be coming from outside or may be provided by the sequencer, and it will give a feedback to the state machine. State machine can also provide some outputs, or the data processing elements will provide outputs, either store them in memory or provide it in the outside world. Let me draw a representation of a FSMD which is useful for implementing single purpose computers. So, here is my sequencer. Here are inputs, and these would turn out to be asynchronous inputs. I would need a clock signal. This is my clock. Here is my elements of data path. These data path elements will get control signals from the sequencer. So, these are control. The data path elements will perform certain operations for which it may have some inputs from the same inputs which are going to the sequencer, or it may have certain other inputs. It will provide feedback, and we call this status. The data path may produce certain outputs for global consumption, that is for the outside world. The sequencer may also produce some outputs if it so wishes, and these two outputs are your global outputs or user outputs. So, this is the block diagram that we are going to use in this lecture, and we will implement a useful single purpose computer. What are the elements of data path? This is not the only 10 elements, this is just a sample of such data processing elements. Usually data path elements are elements of combinational circuit. You can implement elements of data path using simple combinational logic, but that is not necessary. Sometimes you may have to store some information for further processing. So, for that you may require latch and flip flops. Sometimes you want a flip flop with the enable signal, so that you only capture the data whenever the enable signal allows you to. You may use tri-state buffers, you may use comparators for comparing two numbers, you may use encoder and decoder, you may use multiplexers and demultiplexers, and counters, and you can use adders and subtractors, or you could make a generic building block, an arithmetic logic unit which would not only perform mathematical operations, but may also perform logical operations. You could also divide the clock for use in certain parts of the data path, and this is just a sample of some of the data path building blocks. So, here is the representation of a flip flop, and like I mentioned, we do not manually connect all the building blocks such as flip flops or gates, but we write VHDL code to model them. So, for a flip flop here it is a rising edge flip flop, as this clock indicates here, this is the rising edge, and so it is going to capture whatever data here on every rising edge and present it to the output. Here is a VHDL code to represent that. I am not going to go in detail, and I strongly urge you and encourage you to learn VHDL or other hardware description language such as Verilog, and there are many software programs available which you can use to practice and develop logic systems. Here is a control latch, which means it is going to capture information at the rising edge, but only when enable is 1. Let me show you what does it mean. It means if enable is equal to 1, then Q gets the value of D on clock rising edge, else if enable is equal to 0, Q gets the value of the previous value. So, I will call it Q previous, which means it does not capture the input. Now, how does it use a normal D type flip flop? How does a normal D type flip flop get modified to implement such a requirement? Well, this can be implemented as a finite state machine by itself, and you could draw the state diagram for this finite state machine and implement it, and the implementation will look something like this, that it does use a D type flip flop, but it uses an additional component, which in this case is a 2 input multiplexer. 0 and 1 are the inputs. The output of the multiplexer provides the connection to the D type D input of the D type flip flop. Here is the Q which will go to the outside, but it will also be fed back into the 0 input of the multiplexer. The 1 input of the multiplexer is actually the D in, which you want to capture here. So, D in. The clock will be applied to the clock input of the, and the control signal of the select line of the multiplexer will become the enable signal. Now, let us go through this circuit to understand that it actually implements this requirement. Now, if enable is equal to 0, the 0th input gets connected here, and the 0th input is nothing but the current value of the Q. So, on every rising edge it is going to just capture D and transfer it to Q, which means Q value is not going to change. But the moment enable signal becomes 1, now it is going to route the D in input to the Q, and now on every rising edge it is going to capture this value and put it at the output. This is exactly what we wanted. And so, this is the method of implementing a latch with enable signal. Similarly, you can add more signals to this by saying that I want a reset signal, that is, if reset is 1, then irrespective of the rest of the state of the rest of the input signals, the output should be 0, and so on and so forth. And you can implement VHDL code to implement whatever functionality that you wish. Here this is the code for a controlled flip flop, that is a flip flop where there is an enable signal. Then one important building block is the tri-state buffer. Here output gets the value of input provided select line is equal to 1, but if select line is 0, then the output becomes high impedance. Here is a VHDL code for that. This Z here indicates the high impedance, Then you would require comparators to compare digital numbers. Here in this example, two 3-bit numbers A and B are being compared, and a comparator typically has 3 outputs: A is greater than B, A is equal to B, and A is less than B. Whenever any of these 3 conditions is true, that particular output becomes 1 and the others are 0. So, if A numerical value of A, those 3 bits as a number, is more than the numerical value of B, AGTB will be 1 and the rest of the 2 outputs will be 0. If the numerical value of A is equal to B, AGTB will be 0, A equal to B will become 1 and A less than B will also remain 0. Likewise, we can, this is the VHDL code for implementing such a 3-bit comparator, and you can increase the size by having n bits on the 2 inputs. Similarly, this is an encoder which encodes the value here depending upon the combination here of zeros and ones, it provides an output. And you could make a priority encoder, meaning if this is 1, then the value of this will indicate that IN2 is 1 and so on. Here is the code for the encoder. This is the opposite of encoder, this is a decoder. In this case, this is a 4 to 16 decoder, and again VHDL representation for such a decoder. Then we have a multiplexer. This is a 8 input multiplexer. Each of the inputs is single bits, and the select lines here will decide which of the inputs get routed to the output. We use such a multiplexer, 2 input multiplexer, in a previous example, and multiplexers are very useful building blocks, and we are going to see their use in our implementation. This is the VHDL representation. Again, this is a counter, and in this case the counter has a clock and a clear signal, which means if clear is 1, all the bits, output bits of the counter will become 0, else it will count. Now, this does not indicate whether it is going to count up or count down or may have a different counting sequence. That will be decided by the kind of VHDL we have, and as we see here, the count is being incremented on each clock edge. Therefore, this is a up counter, a VHDL code for up counter. This is a arithmetic and logical unit, and there are 2 operands, operand 1 and operand 0, and the opcode, that is the bits here, will decide what operation it performs, and it will depend on you. If you want to do add, subtract and the bits of operand 1 and 0, it will depend on all of you. As you can see here, lot of functions are being performed. Here you are ANDing, you are ORing, you are adding, subtracting, you are incrementing, you are decrementing, and so on. So, you can implement a wide variety of functions using a ALU. Clock divider is used to divide the clock frequency from a higher value to a lower value, and it is often useful in FSMD applications. Now, what we are going to do, this is the VHDL code for a clock divider. What we are going to do is in our next lecture, we are going to implement a single purpose computer to implement a particular requirement, and that is to implement a dual dice game. That is a game in which there are 2 dice outputs, and the rules of the game will be mentioned, and we will see how these are implemented very easily using the finite state machine with data path approach. So, I will see you soon in the next lecture.